Okay, everyone, thanks for coming today, to everyone in here and online. So if you came in person, you got coffee and donuts. That's almost there. So today's talk, we have Giovanna giving a talk. She did her PhD at Virginia Tech and did postdoc at Cleveland Clinic and then NIH as well. Right before she came to CMAS, she was at Muskegon, going back to Ohio, and then love the facility here and doing a lot of cryo work here. I know she's on the Glacios quite a bit, Krios, and often see her in the fifth room as well, working with Dan Huber on some cryo-EM work there as well. So she'll be going to talk today on making the most of your Glacios time.
All right, thank you. And thanks for Dan and Ashley for helping get everything set up today for the hybrid Beyond the Scope webinar. So as Dan mentioned, the talk today is all about making most of your Glacios time. And we have some exciting talks coming up in the next few months. More information about those on the website. Okay, so the purpose of my talk today, I geared this talk for people who are just starting out in Cryo-EM, and they just had their initial training session on the Glacios, but they're still not sure of what it is exactly they're supposed to be looking for. So hopefully by the end, Cryo-EM users will have a better idea of what to look for and how to effectively screen their samples on the Glacios. And by being effective on the Glacios, it will help you down the road when it's time to collect data on the Krios and for your Cryo-EM data processing. So I didn't want to be too boring today, so this is a short talk, so feel free to ask lots of questions. For those that are attending live, just feel free to raise your hand and shout things out. For people attending the Zoom, you can use the buttons shown here. Hopefully, I can move.
You can click minimize on that.
Okay. Okay. So you can use the Q&A, chat, or raise hand functions. And if you have some in-depth questions, feel free to stick around after the talk today, or you can also email me. If you're having any technical difficulties with Zoom, use the chat function, and we'll try to get those sorted out as soon as we can. Okay, so here at CMAS, we have a lot of exciting instrumentation. So building off of the Beyond the Scope webinar we had last month, Dan Huber mentioned the Helios 600 dual beam. We do actually have cryo capabilities on that. So if you have samples that you're interested in viewing in Cryo-EM, but that may be too thick for Cryo-TEM, feel free to contact either myself or Dan Huber. We can actually cryo-fib mill them and then from there transfer them into either the Glacios or Krios, all under cryo conditions. So it's very exciting. Pull this up. Okay. So as Dan mentioned in the introduction, the instruments I spend the majority of my time on are here, the Glacios and the Krios. So here at CMAS, we're actually very fortunate to have a Cryo-TEM dedicated for screening samples. This frees up a ton of beam time on the Krios and lets the Krios do actually what it's intended for, and that's collect lots and lots of high resolution data. So again, the goal of my talk today is to show you how to effectively manage your time here so that you get the best possible data coming from here. After seeing this exciting list of instrumentation, and then seeing all this list of capabilities that we can do here, if you're interested in learning more, there are several ways you can do that. One way is by doing exactly what you're doing now and attending a Beyond the Scope webinar series. You can also schedule a one-on-one consultation with any of the CMAS staff members, and I'll be happy to help get you started with different experiments. Here at CMAS, we also have some limited connection to our data analysis computers. So once you have your data, we can also help you process it. So contact cmas@osu.edu if you're interested in learning more about what we have. Dan already gave a pretty good introduction, so I'll just repeat almost exactly what he said. So I dual majored in biology and chemistry, got my bachelor's degree at Walsh University in North Canton, Ohio. I started graduate school at the University of Cincinnati and then moved to Virginia Tech with my advisor, where I got a PhD in chemistry. And during graduate school, I did a lot of fluorescent microscopy and flow cytometry work. Toward the end of graduate school, I started doing a little bit of TEM on resin embedded cell samples and had a lot of fun doing that. For my first postdoc position, I worked at Cleveland Clinic. I trained other users how to do fluorescent microscopy, and in exchange, I got trained with how to do more molecular biology techniques. So PCR, cloning, things like that. My second postdoc was at the NIH, and here's where I really got into electron microscopy. So I did a lot of Cryo-EM and room temperature TEM, and I've also done a fair bit of room temperature FibSem on resin embedded samples. And at the NIH, I was able to combine some of my fluorescence microscopy background with EM and develop some pipelines for correlative fluorescence and electron microscopy, which is what's shown here. So here we have some fluorescently labeled Ebola virus particles. And then I know exactly which cell to look at in the FibSem, and I'm able to find my little Ebola worms very easily. After my postdoctoral work, I accepted a position with Leidos, and they're a contractor for the NCI. And the work I did at Leidos was very similar to the work I'm currently doing here at CMAS. I focused mainly on sample preparation and screening samples for single particle Cryo-EM. So again, the majority of my work was done on the sample preparation and screening side. After that, I worked as an assistant professor of chemistry at Muskingum University, an hour away from here in New Concord, Ohio. I spent 3 years there and then came back to microscopy, and I'm now at CMAS. And I've been here for about 1.5 years now. So Cryo-EM, there's a long process from going from your sample in your Eppendorf tube to a beautiful high resolution structure. So it all starts with the sample prep. In order to move your project forward, your sample has to be pure. So I highly encourage using as many methods as you can to screen your sample before getting to this stage. Once you have your sample, it's pure, it's exactly what you expect it is. You can then freeze your sample and get it on the Glacios. From here, you can expect to spend several rounds of sample optimization before your sample is ready for the next step, which is data collection, followed by another long process, which is data processing. Again, the last beyond the scope I gave was all about troubleshooting your sample prep. So this stage, so now I'm going to focus more on this stage, what to do once you're actually on the Glacios. As I mentioned earlier, before you even get to the Glacios, your sample has to be pure. There are many different ways to check purity, but not a lot of ways to check structure. Particularly for users who are new to TEM and new to structural biology, I recommend doing at least one round of negative stain because it's a fast and easy way to check your sample before Cryo-EM. And a lot of times you can rule out problems before you even get to cryo. So if you're seeing mystery particles or if your particles are falling apart, it's better to find out in negative stain than it is to find out with the expensive cryo microscopes. We recently installed serial EM on both of our Tech9 microscopes here. This allows us to collect hundreds of images very quickly. So I timed it on the TF20 and was able to collect 100 images in 6 minutes. So this allows you to get very, very fast answer on whether your sample is pure enough for Cryo-EM or not. Once you have that stack of 100 images, you can then get preliminary 2D class averages. So then you have an idea of your particle size and shape, so that once you get to the glacios, you're not stuck scratching your head wondering, is this my particle or is this just debris? So it's always a very good idea to have an idea of what your sample should look like before getting to the glacios. So once you have some beautiful negative stain results, you know exactly what you're looking for in Cryo-EM. I spend the first round of cryo screening optimizing my blotting conditions. So when someone hands me a tube of protein and says, I want Cryo-EM data on this, the first thing I do is try to get my ice conditions just right. For the first round, I don't make too many grids at once. The longer time you spend trying to freeze your grids and clip your grids, the longer they're exposed to air, and this can lead to ice contamination, particularly if you're new to Cryo-EM. So if you're new to Cryo-EM, you're still learning how to handle grids and how to work under cryo conditions, I recommend starting small. Main reason is to eliminate ice contamination. And then for me personally, I start small because I hate guessing. I don't want to just throw a bunch of samples and bill users for using a ton of grids and a ton of hours on the glacios only to have not so great results. So I'd rather do smaller, less expensive sessions and then have a better idea of how to move the project forward. So for the initial one, someone hands me a tube, I usually just start with 4 grids, and then I use 3 microliters of undiluted sample per grid. And then I pick one parameter on the VitraBot to alter either blot force or blot time. Unfortunately, I don't have a one-size-fits-all blotting parameter that works for every single sample. So when I'm training users on the VitraBot, the 2 starting points I'm always sure to include are blot force of 0, blot time of 3 seconds, and a blot force of -5, blot time of 3 seconds. And these 2 parameters usually give me a pretty good idea of whether I need to go longer or shorter on my blot time. So I look at the ice thicknesses of these 2 parameters first. Once I have blotting conditions that work, then I focus on optimizing my actual sample. So the main thing I try to optimize next is concentration, and then later down the road, sample behavior. So now you've done the VitraBot preparation, you've made your grids, and you're sitting at the glacios. What I look for first is, do I have thin, usable grid squares over the majority of the grid? So one thing you can do to really help optimize your glacios time is by planning ahead. So look ahead at the glacios schedule and provide staff with notice. And if we have enough notice and if the glacios schedule permits, we can collect atlases of your entire grid, so that when you're sitting at the glacios, you can quickly look through all of the atlases and not waste any of your screening time on grids that you know for sure are not going to be usable. Of course, this isn't always feasible. I know grad students are very, very busy. So even if you can't collect full atlases, the next best thing is to spend time looking over the entire grid. Don't screen on just one section of the grid. To quickly screen through your whole grid, you can use the freeze screen and the stage squared function and just double click to move the stage around. And I usually take low magnification images of the top, bottom, left, right corners and the middle. And that gives me a pretty good overview of whether my blotting conditions are good or not. So people who are new to Cryo-EM often ask, well, what is a good grid square? So I look for grid squares with slightly rounded corners. If you see sharp corners, that's a good indication that the ice is either too thin or there's no ice at all present in those samples. If you're plotting with the VitraBot, you'll have a gradient of ice thicknesses across the entire grid. The smaller the square, the thicker the ice. So for data collection, ideally you want thin ice. So how many good squares do you need for a data set on the Krios? Then unfortunately, I do not have a hard and fast answer for that, because it's highly sample dependent and it's highly project dependent. So it depends on you. So what biological question are you trying to answer? What resolution do you need to answer that question? And again, it's also sample dependent, because you can have a lot of good squares, but how many usable holes per square and how many particles per image do you have? So again, it's going to take some careful screening and not just a simple counting grid squares to make sure to move on to the Krios. As I'm screening, if I come across ice that's too thick or too thin, I don't spend any time collecting higher magnification images. I mean, the main goal for my initial screening sessions are to optimize blotting conditions. So if I see grids that are either too thick or too thin, I just move on to the next grid in the autoloader and don't spend any of my precious screening time trying to squeeze information from grids like this. Trying to force high magnification images on a grid, particularly a grid that's very thick, can give you misleading results and often be a waste of your screening time. So if you see grids like this, I recommend just moving on and going to the next one. As I'm screening, these are a few questions that I ask myself during the process. So the first question I ask is, does the majority of the grid have good grid squares? And for good grid squares, it's a matter of ice thickness. If the answer to that question is no, I immediately load the next sample and don't waste time. If the majority of the grid looks good, then I move on to the next setting in EPU, which is the grid square mat. So EPU provides a way to quickly move through magnification and imaging settings. So do my grid square images look good? If that grid square I'm on looks good, then I'll go on to the next EPU magnification setting. If not, then I immediately move on to the next grid square. So again, it's not worth the screening time to fight a bad sample trying to get good images from it. I repeat this process for grid squares at different ice thicknesses, because protein samples can behave differently depending on how thick or how thin the ice is. And I'll talk about how that is in the next few slides. Also, taking all of your high mag images from just one grid square can be very, very misleading. You might think that you're saving a lot of time and money by just taking a few images on one grid square and then moving straight to the Krios. But images from that grid square may or may not be representative of the entire grid. So it's a bit of a gamble to do things that way. Again, as I'm moving through the different magnifications, I'm looking at the ice over each individual hole. And then finally, we get to the high mag images. And when I'm at the high magnification, I take high magnification images of the edges and the middle of the holes to see where my particles are. And if I don't see any particles, then I'll take some images on the carbon to see if they're sticking there. So more detail on what to look for at each of those EPU settings. Again, if you're using the VitraBot, there's going to be a gradient of ice thickness over the entire grid. Collect images at different ice thicknesses so that by the time you get to the Krios, you'll know exactly which grid squares to focus on for picking holes. The less time you spend hunting and searching on the Krios, the more time you have for actually collecting high resolution data images. So the things I look for at this magnification are clearly defined holes with slightly fuzzy edges. If you see clearly defined holes with very sharp edges, there's a good chance that those holes are actually empty or have ice that's too thin. Squares that look good at the Atlas magnification might not look that great at the grid square magnification. Get that out of the way. So you can see this square, for example, it's got the nice rounded corners, but it's got a patch of really thick ice in the middle. So that's going to hurt data collection. Another thing that I do while I have the microscope at this magnification setting is to use the wobbler and flue screen to set eccentric height manually. So don't be entirely dependent on the EPU auto functions. There's several reasons for this. One reason is some things are easier to see for yourself Yes.
Just really quickly, what does EPU stand for?
It stands for E pluribus unum,
Oh,
and that is Thermo Fisher's software that they use for Cryo-EM data collection.
Oh, okay.
Sorry about that.
No.
So yeah, so on both the Glacios and the Krios, we use Thermo Fisher's EPU software, both for screening and data collection. So back here, I highly recommend that users set your center height manually because some things are easier to see as the stage is tilting rather than when the stage is flat. So as the stage is tilting, I look for shimmering over the grid squares. It's very common to see shimmering over the edges of the grid square, and that's normal. That's a sign of crystalline ice. But if I see a lot of shimmering in the middle of the grid square where my holes are, then I know, okay, I'm just going to move on to the next grid square and I'm not going to spend time here because the ice is not good. Another thing to look for as the stage is tilting are cracks. Some cracks are very difficult to see at a stage tilt of 0, but as it's moving and tilting, the cracks become a little bit more obvious. So if your grid square has a lot of cracks in it, as you're collecting data, that's going to cause a lot of drift, and the images that you get from that grid square are not going to be usable. So look for cracks. And then the other reason why I strongly encourage users to set U-centric height manually first is because it does end up saving you time. And if you can just manually get it in the ballpark where it should be, the EPU auto function will go a lot faster. Versus if you just load the grid into the column and go straight to the EPU auto function, it's going to take a long time to find U-centric height. So you'll save some screening time just by taking an extra minute or two to set U-centric height manually. As you're screening, save images of the grid squares and keep track of which high magnification images came from which grid square. Because again, this is going to help you later down the road when you're on the Krios. Because again, the less time you spend hunting for good grid squares on the Krios, the more time you have for actual data collection. So now I've looked at my grid square and I've looked at it while tilting, and I know that this grid square looks very promising. So now I'm going to go down to the whole U-centric height in EPU. Then here I move to a spot on the carbon, and then I redo the auto U-centric height and autofocus with EPU. And it's important to do that every time you move grid squares. I guarantee you your grid is not perfectly flat. So when you move grid squares, the U-centric height is going to be slightly different. So when you're taking your high magnification images, you want them to look good and be in focus. So take a few extra minutes to do those steps. Also save images at this setting as well. Look for your ice distribution across the holes. So here you can see I've got some holes that look promising. I've got some holes that are empty. And I've got some holes with very large holes or cracks in them. So you want thin ice over the majority of the hole, but you don't want your ice to be too thin or else it's just going to crack and melt during data collection. So it's a delicate balance. So questions to ask yourself are, is the ice uniform over the entirety of the hole, or is it thicker toward the middle or thicker toward the edges? And again, this is very sample dependent. The two most commonly used grids for Cryo-EM prep are quantifoil R22 and quantifoil R1.2, 1.3. There's pros and cons to both. R22 has a larger hole diameter. It's harder to get more uniform ice across that entire hole. You'll have more of a gradient of ice thickness. The benefit is you can also do multiple shots per hole during data collection. So within your 24-hour data collection time, you can collect more images, but are those images going to be good? Because you're going to have a gradient across them. Versus the R1.2, 1.3, they have a smaller hole. It's easy to get uniform ice, but the data collection can be a little bit slower because you're often limited to 2 shots per hole, or in some cases, only 1 shot per hole. So once you know that you have good ice and your blotting conditions look good, the next thing to screen is your actual sample.
Just on, so for these, for the holes, how much time can you actually spend imaging on them? we're not, obviously I'm not a biological TM person, so how much dose can you put? Because I'm used to being able to image on the sample for days. So,
Not very long, so I usually take a whole image
mhm,
and it doesn't put hardly any dose on your sample.
mhm,
And then I move and go straight, if the holes look good, then I'll go straight into taking an image in the center and on the edges of the holes.
mhm,
And then I'll move to the next area or the next grid square and then take one full image, and then the majority of my screen time is actually spent at the higher magnification setting.
yeah,
So it doesn't take too much time, just a few seconds,
mhm,
but I encourage users to do that stuff because it then saves you time when you get to the Krios.
mhm,
So I encourage users to take high magnification images in areas of thick ice and thin ice, because you want to see how your particles are behaving and what your data images are actually going to look like. So this is your chance to get a little bit of a preview of what your Krios data is going to look like. So things to look for are, how many particles per image are you getting? Do you see any signs of aggregation? Or do you see any signs of preferred orientation? Then take high mag images in the center of holes and around the edges of holes. Because when you're setting up your data acquisition, you can tell the camera to either be here or here. And you want to be where your particles are. Plan ahead for data collection. So you have a grid, and you think, well, the ice is a little bit on the thicker side, but I think I can still squeeze out some data from this. And that's fine. But you have to ask yourself, is it worth spending the time to have 24 hours of Krios data collection and the extra processing you'll have to go through to try to squeeze out a structure? Or is it more worth your time to maybe reserve an extra round of screening on the Glacios? So it's going to depend on your project, and it's going to depend on your project goals. So as you're screening your high magnification images, look at the signal to noise ratio. If your ice is too thick, it's going to make particle picking very difficult, and it's going to make the resolution of each image lower than it could be. So it's still workable, but it's not optimal. And if you're spending the time and money and collecting terabytes of data, you want to make it worth your while to process that data. So again, what to look for. You want a lot of particles per image. You want clear definition around each particle. So there has to be enough space around each particle so that as you're doing your particle picking, you know you're picking individual ones. And have a good distribution of different orientations. Again, collect as many high mag images at different areas of your grid as you reasonably can within your Glacios screening session. Just collecting images from one area of the grid is not going to give you a good enough picture of what the rest of your data is going to look like on Krios. As you're saving your high magnification images, save them as either TIFF or MRC, because these don't have any compression in them, and then you can use them later to do a test processing run and see if it's easy for you to pick particles and generate 2D class averages. During these high magnification settings, this is where you really get to know your sample. So you should know how your sample is distributed across the whole. Ask yourself, are multiple shots per hole feasible, or would I be better off collecting one shot per hole? So again, multiple shots per hole, it's faster, you get more images per data session, but if the images aren't good, is it worth having those extra images? Or is it better to have less images, but know for sure that each of those images are going to be good for data processing? Also, take a look at your protein concentration. So I've been talking about aggregation. So is my concentration too high? On the other end of the spectrum, is the concentration too low? If I don't have a lot of particles per image, it's going to take a longer time to collect enough data to give me enough particles to get a structure. And so at that point, is it worth reserving extra days on the Krios and spending thousands of dollars? Or is it worth going back to my sample prep bumping up my protein concentration and using another few $100s of Glacios screening. So again, that's up to the individual user to decide. But by the end of your Glacios session, you should have a very good idea of how to move your project forward. So you'll know whether or not you need to adjust your blotting conditions, how to adjust your protein concentration, and how your particles are distributed. So are they behaving the way that you want them to? You should also have an idea if your grids are ready for the Krios. So again, there's a balance here. I understand that deadlines happen. Sometimes you just need something very quickly. Is it worth your while to move forward to the Krios with maybe a grid that's not as perfect as you'd like? There's a saying that says, don't let perfection be the enemy of progress. That's also something to keep in the back of your mind. So there comes a point where with Glacios screening, you do get some diminishing returns. If you're trying to go for perfection each and every time, is a lower resolution structure good enough to answer your biological question? Do you absolutely need a sub-2 angstrom structure? So hopefully by now, have a better idea of what to do once you're sitting at the Glacios. It's normal to expect a few rounds of Glacios screening prior to finding a grid good enough to go into the Krios. The order that I usually go in is first optimize blotting conditions, then I optimize my concentration, and then I optimize sample distribution. So again, if I see things like preferred orientation or everything is sticking to the carbon or not going evenly through the holes, there are ways we can troubleshoot that. Unfortunately, there's no one-size-fits-all set of rules that will work for every sample. Each and every cryo project is going to have different blotting conditions and different data collection parameters. But if you spend some time carefully screening your sample, you can almost guarantee that the data coming off of your Krios is going to get you some structure. The worst case scenario is to rush through Glacios screening, get to the Krios, spend $1,000, have 2 terabytes of useless data. So this is what I would like to avoid at all costs. If you ever have any questions, CMAS staff are here to help. You can reach out to me directly at my email address, or if you just want to stop and chat about Cryo-EM, I'm always happy to talk about different sample preparation methods. So that's the end of my talk. Hopefully you can join us over the next few months. We have some pretty good talks coming up, and to register for those and to find out more information, you can go to the website shown here. Also, we hope that you stay in touch with us. You can view all of our previous Beyond the Scope webinars on YouTube, and you can also keep up with the latest and greatest CMAS events through social media.